Okay, so assignment 4 has been moved from last night to tonight. So if you've already turned it in, you can always make changes, but otherwise you can still work on it. And I won't download your versions until this evening, which will delay their grading a little bit for a few days. But and also I put up assignment 5, which is due in about 2 weeks. And assignment 5 deals with our new topic that starts this week, linear maps. And there are 3 new sections: maps, linear maps, and isomorphisms. They're all due in 2 weeks on, I think, a Monday night or Sunday night. I'm not sure which. About the same time that assignment 5 is due. So assignment 5, um, yeah, this isn't due on the 21st. This is due, oh, it is the 21st, tonight. Yes. Okay. So that's what we are. And so our first topic in the course dealt with linear systems. The second one dealt with vector spaces and subspaces, linear independence, and linear maps are maps between between vector spaces. So let's start with this, and it's chapter 6. And the first thing we have to deal with is just reviewing or recalling or learning about ordinary maps between arbitrary sets. And then we'll deal with linear maps, which are maps between vector spaces. Okay, so we have the topic of maps. And basically, this information is the same as it was in, if you've taken CS 205. This is the same, basically the same information. So we have 2 sets, which will eventually be vector spaces, but let's think of them now as just finite sets. We have a domain, and we have a codomain. And it can be a set of any elements, any sort of set, and eventually we'll have vectors, but we just want to introduce the idea of maps in a simple context. So here's 2 sets. They don't have to be the same set. In fact, let me make them so they're not even, don't have any elements in common. There. So this one has 3 elements, this one has 10 elements. When we do vector spaces, they don't have to be the same kinds of vector spaces, or even the same, like if they have a basis, the basis they don't have to have the same number of elements in the basis. They don't have to have the same dimension. Okay, so a map has a domain and a codomain. Say we have the map F, and what a map is a dependency relation. Well, let's call it M, since to recall that it's a map. Okay, so it's an association for each element of the domain. Each element of the domain is associated with, or goes to a single, is associated with a single element of co-domain. And one picture of this is as an arrow diagram, so we can go like this. So the idea is each element here, to be a well-defined map, each element here has to have an arrow coming out of it. That means you have to associate some element in B. Every element of A has to be associated with some element in B, but it can only be associated with exactly one element. You can't have it associated with 2 elements. Now, the elements of B, like this number 7, don't have to be associated with anything. In fact, here you couldn't have a map that associated every element of the codomain, because there's too many of them with this. So what being a map rules out is a domain element going here. This is ruled out this. So you can't have like 1 going to 10 and 7. Like you couldn't have 1 going to 7 and 10. That's ruled out. Because each element of in the domain has to have a single element over here, but it has to have 1. The second thing that's ruled out is, say, 1, no arrow. That also wouldn't be a map. Okay, so we can express this definition of a map more formally by saying that for every x in A, this is, remember, this is upside down A for all or every members of A, there is, well, let's give it lowercase a for the elements of A. There is a B, member of B, such that B equals F of A. Okay. So this says that for every element of the domain, there has to be a B such that B is the target of F of A. Okay. But the second thing, this property rules out number 2 here, that there's no arrow. This is the no missing arrows. Okay, the second property is, if you imagined taking 2 elements here, okay? So for every pair of elements, B1 and B2, that are a member of B. So you could sort of imagine randomly sort of being blindfolded and choosing 2 elements of B, and you'd say if then B1 is not equal to B2, then well, then maybe I have to say this differently. Let's do it the other way around. For every element A, you choose 2 elements of the domain, A1 and A2, member of A. Then if, so you've randomly chosen 2 here. Now, if A1 is equal to A2, you might have chosen, like you could have 2 people choose ones, and they might have chosen the same element or different elements. And if they happen to choose the same elements, then it has to be that I'm using F here, which is doesn't correlate with, started with F, but then chose the name of the map to be M. Then M of A1 has to equal M of A2. Okay. Now, what this notation here, maybe, for example, if for this M, we can say, we have this notation that's sort of like M of 1. This is like the functional notation that you're used to from math, like F of X equals 2X. Well, if I put in 1 here, I get out 2. This F of 1 is equal to 2, F of 2 is equal to 4. So this is the same thing. M of 1 equals 10. M of 2 equals 9, and to be complete, say M of 3 equals 8. So this just is pairing up, showing you the element of the domain here, and M, you can sort of choose any domain element here, and you get out a codomain element. So this is sort of the input-output machine version of maps. Well, here this is notations being used here and here for the image of A. Okay. Now this um, may seem a little, it also works in, if I sort of say, well, an equivalent of this, which makes it a little clearer, if I choose two elements and M of A1 is not equal to M of A2, that is, if the target elements are different, then A1 cannot be equal to A2. So there's two sort of versions of this. If I, and either one of these are logically equivalent. They're called contrapositives of each other. And this is, again, a little bit of logic, but the point is that this rules out condition one, because you can say, okay, if I have, this says that if I have M of A1 here, and it's not the same element in, these are members of the codomain, and if they're not equal, right, they're shown differently, then they can't come from the same element. They have to come from A1 not being equal to A2. So this is the situation that has to occur. So if this is true, then this is true. This one starts the other way around. It says if it turns out that these two are the same, you can't have these be different. They have to be the same. So you can see that they're really dealing with sort of two ways of looking at the same condition. Okay, well those are the sort of the probably this is more logical notation than needed, but they give you the idea that you can think of it intuitively, and there's precise definitions, and these precise definitions are useful because we're going to be looking at properties of maps, and those properties will carry over to the case of vector spaces. So here we have the first. This is if these two properties hold, you have a well-defined map. So there is some concept to a map, not just any. Let me put the wrong page. Okay. So if these two properties hold, you have a well-defined map. Now we're going to be interested in two properties of maps, and those properties have the names of onto and one-to-one. And then if both of them are combined, a map that if both hold, then the map's called a correspondence. Sometimes you say one-to-one corresponds to emphasize that's sort of the important point. So let's look at these two properties. You can sort of identify them. Let's use the same or similar map before. Let me draw the arrow, repeat the arrow diagram so you can see here. It doesn't matter what the elements are. These are like three elements here in A and three elements in B. Now, if, let me do, change it a little bit. Say B has three elements and A has four elements. Okay, then see, every element here has to have an arrow coming from it. So this one has to go somewhere. Say it goes up here to this first one. Okay, well this map is this map N is onto. because every element in the codomain has an arrow pointing towards it. So every element in the codomain is an image. We say if if you have b equals f of b equals n of a, n of a, so a gets mapped to b. Like if this was a and this was b, then we'd say n of a is b. This is also called the image of a. So this onto means every element of codomain every element of codomain is an image of some domain element, which holds this. You don't have, no, like for example, the first map here, M, is not onto. M above is not onto, because nothing points to 7. Okay, it can't, it's impossible for a map between A and B to be onto, because it couldn't be a map and still be onto, because this has too many elements. So this is you can sort of see this is going to be not onto. And again, there's a sort of precise way of saying, you can sort of translate these words for every element B, member of the codomain B. There exists, no, we want it the other way around. Not exists. We want for every element of the codomain, there exists an A member of the domain such that f of A equals B. So that for every B, this is just saying these words. It's a domain. Some element of A points to it in an arrow diagram. Okay, so that deals with onto, where every element of the codomain has an arrow pointing to it. And then there's a second property, one-to-one. Okay, so a one-to-one map, let's look at what the one-to-one map is. Let's look at just the ones with, we can still have this situation here. We can say here, okay, this map MNP, P is one-to-one. One-to-one means that no element has two arrows pointing to it, okay? No co-domain element is the image of two different domain elements. Okay, so for example, here, there's no, you can see, for example, since this one here, this map is not onto. So if you can have a map that's not onto and is one-to-one, right? Because there's no bunching up here. This is not onto because this second element down does not have an arrow pointing towards it, but no arrow has two arrows pointing to it. Now let's look back and see if the previous maps are one-to-one. Now this one is onto because every element has an arrow pointing towards it, but N is not one-to-one because this first element has two arrows pointing towards it. So this element is the image of two different domain elements, so it's not one-to-one. And our first map up here This one is one-to-one. It's not onto because 7 doesn't have a one, but it is one-to-one. So this is a map that is one-to-one but not onto. Sort of similar to this. You can also have a map that you can have maps that are one-to-one and not onto, and you can have maps that are onto but not one-to-one, and you can also have maps that are both. Well, let's first do the formal thing of this one here. What you want, the way to say it is, are for every say A1, A2, for every 2 domain elements, right? If f of A1 is equal to f of A2, then it must be the case that A1 equals A2. What this rules out, rules out f of A1 like this, because it's saying, okay, if you just randomly choose 2 elements of the domain and look at their images, if the images are the same, you must have chosen the same element, because if they were different elements, then it wouldn't be one-to-one, because you'd have 2 elements pointing to 1. Now, this one is similar, if you notice, to the property here. But this is the other way around. It's A1 equals A2 going to the function here, and this starts with, but I keep using F. I guess I should have used F from the beginning. This is for dealing of, well, it doesn't matter for this, this is saying that F is the map for all. If this holds, then F is one-to-one. This is the one-to-one property. Okay, well, you can see that it's the other way, it's the converse, the other way around. If I said A1 equals A2 implies that, that's just the condition for a well-defined map. So this is the condition for being one-to-one, and it's a turned around version of a well-defined map. Okay, and there's also you can also look at the contrapositive. It says if A1 is not equal to A2, like if this situation did occur here, that would have to imply that f of A1 is not equal to f of A2. This would say, okay, if A1 and A2, your domain elements, are not the same, then then f of A1, those cannot be equal. So this first version rules out this. This version says it also rules out this by saying, okay, if these are different, then these have to be, if the domain elements are different, the images have to be different. Here it says if the images are the same, then the elements they come from have to be the same. Okay, they're just 2 different ways of looking at the same thing. Okay, well, then the last one is, what if you have both one-to-one and onto? Those maps are called correspondences. Okay, so let's look at one of those and see what the implications are for that. Here's a domain. Here's a codomain. Now, the point is, you have an arrow coming out from each of these, and since it's onto, since you only have 3 elements here, you have to have the same number here, and you can't bunch up. So you have to have, so this one is one-to-one and onto, because every element of the codomain has an arrow pointing towards it, and every element, and no element has 2 of them. Okay, well, that's the story on maps, one-to-one and onto maps. Let me